All right, so these days we have really strong bases like LDA. And LDA is a really powerful synthetic tool that can make these enolates and enolate equivalents quantitatively. But it wasn't always that easy. One, two, LDA is a little bit more dangerous than the bases that we're used to, like hydroxide or ethoxide, some of these other O minus bases. Those are a lot safer to deal with. So while LDA can make things easy, there wasn't always access to LDA, and sometimes it's just easier to use more safe reagents. So first of all, let's take a step back. What did I mean when I said LDA makes things pretty easy? Well, if we wanted to take this molecule, ethyl acetate, and turn it into this molecule, how are we going to do that? Well, we can note right off the bat that we've added 3 carbons to that. So how would we do that? Well, we need to make this position nucleophilic, and we have to add those 3 carbons. So we could easily do that by treating this molecule with lithium diisopropylamine, so that really strong base. Again, we have to use our ethereal solvent and keep the reaction cold. And once we do that, we would form our enolate. And that enolate is formed unidirectionally because this is such a strong base, right? This pKa here is about 20, and the nitrogen that was just protonated, here's the conjugate acid of LDA, that pKa is probably about 38. So this is a much stronger acid, so the equilibrium goes that direction very easily. Then we add our second reagent, those 3 carbons, and then a halogen on that, and that's just going to undergo a very nice, easy substitution reaction. So LDA makes things really easy. How else could we do this? We could theoretically do this with a weaker base, like ethoxide, so something like this, or potentially try tert-butoxide. But what did we say earlier? We said earlier that the conditions to do that are really kind of challenging, because if you mix ethoxide with that alkyl halide, they can just react in a substitution reaction. If you mix this tert-butoxide with that alkyl halide, they can just react in an E2 reaction. So if we instead are able to quantitatively form our enolate, and that's the only thing that's a strong nucleophile, or it's at least like by far the strongest nucleophile around, then this substitution reaction is going to happen a lot easier. So LDA makes things easy, but before LDA, there were still ways to make this type of molecule, and things just were a little bit less clear as far as like we can see very easily how that goes to that, but what I'm going to tell you about now is that chemists used to use something called a Malonic Ester Synthesis to make that same type of molecule. And what I want to point out to start out is that essentially what we have there is this. So this extra stuff we didn't want, maybe we wanted to synthesize that molecule, and we've synthesized most of it, right? We have 1, 2, 3, 4, 5 carbons there, 1, 2, 3, 4, 5 carbons there, and then we have the ethyl ester, the same ethyl ester on the other side. So we have the same pieces, but we just have some extra stuff. So why do we need this? Why is this going to make the reaction easier for us? Well, let's compare the acidity of this proton to that proton. We said that pKa is about 20, whereas this one, what's this one going to be? Hopefully you guys remember that having 2 carbonyls, a 1,3-dicarbonyl, drops the pKa about 10 units. So this pKa was about around 20. This pKa is going to be closer to 10. And let's put about, not exactly 10. So where something like ethoxide or tert-butoxide was not strong enough to fully deprotonate that, making the enolate, when we have 2 carbonyls on either side of the proton, the pKa is much lower, the hydrogen is much more acidic. So if we did treat this molecule with sodium ethoxide, and we can even do that in ethanol as our solvent, that is going to lead to a unidirectional formation of that enolate. So we would have this as our product, and we formed ethanol. So yeah, again, the pK of ethanol, you guys all know that one too. That's 16. So why was this reaction downhill? Because we had the stronger acid, and we're moving away from the stronger acid to make our enolate. Once we have that enolate, again, why was it so stable? Why is that pK so low? Because this negative charge, this one is only delocalized onto one oxygen. This one's delocalized onto that oxygen and that oxygen. So that extra delocalization makes the conjugate base more stable, which means that the starting acid is stronger. So at this point, how are we going to add those same 3 carbons to this molecule? The same exact way. So the first thing we did was we formed the enolate. The second thing we're doing is we are treating that enolate with that same alkyl halide. It's going to do the same substitution reaction to produce that final product. So we can make that same thing. So now the question that you guys all have probably is, well, that's cool, Matt. That's cool that we can do that. That's cool that the 1,3-dicarbonyl makes that enolate easier to form quantitatively. But we still have all this stuff. And if we wanted that molecule, why would we make that molecule with a bunch of stuff on it? And it turns out, and I often in the notes at this point kind of circle this and say, well, we wanted this. This is kind of the garbage. And it turns out that there's a really quick and easy way to get rid of that garbage. So that's good. And we're going to learn about that really soon. But essentially, the last thing I have on this page of the course notes says the malonic ester. This is the malonic ester. It's kind of the common name of that molecule. Allows us to blank form the blank. So the malonic ester allows us to completely form the enolate with weaker, more common, more safe bases. So that's what I have here. The malonic ester completely allows us to completely form the enolate with weaker, more common bases like ethoxide. But the next question is, well, how do we get rid of the garbage that we don't want? How do we get rid of that stuff? More on that in a minute. So this is what we wanted to make. And if we wanted to use a little bit less reactive reagents, safer reagents, maybe we choose to do a malonic ester synthesis instead of using that LDA. So that being said, we said we want to have 5 carbons off of that ester. We start out with just 2 carbons. We added the rest of the carbons by first deprotonating with sodium ethoxide and ethanol. And then we added our alkyl halide, and that put the carbons 3, 4, and 5 onto that malonic ester. So what do we do now? It's a reaction called a decarboxylation, and it essentially allows us to remove that stuff that I called the garbage. So carboxylate, that's a term for a carboxylic acid. So it turns out that what you have to do to remove that group, that garbage, is first form the carboxylic acid. So we have to do that to both sides, right? They're equivalent types of molecules. It's an ester and an ester. So how do we turn an ester into a carboxylic acid? We can either do that under acidic or basic conditions, but we'll just do it under acidic conditions. So we'll say we're mixing this with H3O plus and H2O. What that does is it's going to hydrolyze those esters. So now we have a dicarboxylic acid. And then essentially all we have to do is heat that dicarboxylic acid. So we're going to take this and we're going to heat it. So why does this work? Okay, so I'm going to redraw this molecule, just turning this around. So essentially we're flipping this. These two atoms are going to be flipped, so we're just rotating around this bond here. So that's going to look like this. And what happens when we heat it? Well, it goes through this cyclic six-membered ring transition state where that pi bond is going to break and grab that hydrogen. This oxygen-hydrogen bond breaks and forms CO2, so the C has two O's on it, and then this bond breaks and goes to form a double bond there. That makes that molecule right there plus CO2. So why does the heat help us with this process? The heat helps us because this is entropically favorable. We went from one molecule to two molecules, and we know that heat makes entropy more important. What about this? How does this relate to the final product and to the carboxylic acid? Well, this is just the enol form, which we know is the minor form in this case that would tautomerize to the keto form, which I think I may have lost a carbon. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so there we are. We have our carboxylic acid. We didn't want necessarily the carboxylic acid, right? We wanted the ester. So how do we go to that ester? We take that carboxylic acid product from this step, and we're just going to use our Fischer esterification conditions that we talked about in a previous chapter to re-add that ester. How did we do that? It was just acid, so we'll say H+, so maybe a little bit of catalytic sulfuric acid in ethanol, and that is going to, that acid will catalyze the transformation of the carboxylic acid to the ester. So if you're having a hard time remembering that, feel free to go back to that last chapter where we talked about that. So decarboxylation, that is how we take this molecule, remove that garbage, and get back to the molecule we really wanted at the start. And anytime we have a 1,3 dicarbonyl and one of them can be turned into a carboxylic acid, that decarboxylation is possible. Other important point again, the heat was necessary because entropy favors the products because there are two products, CO2 and the decarboxylated molecule. And what I have written in the course packet is that the reaction scheme above is known as the Malonic Ester Synthesis, and it allows us to prepare functionalized carboxylic acid derivatives. So here's our functionalized carboxylic acid derivative. We can take that functionalized carboxylic acid derivative and make any other carboxylic acid derivative we'd want based on all of those different transformation reactions that we've learned about previously. And it has 3 steps, right? We deprotonate to form the enolate. That's step 1. Then we alkylate, and we did that with propyl chloride. And then we hydrolyze and decarboxylate. So those are the steps for this Malonic ester synthesis. Steps 1 and 2 you can do 1 time or 2 times. This time we did it just once, right? We formed the enolate and we alkylated. But there still is technically an additional proton here. So if we wanted to form another enolate and put a second R group here, that would be a possibility as well. And we'll talk more about that soon.